you produce here will be within brackets.
We don't have that rule here.
Plus, yeah, plus she has another point. We don't have the rule that says equals to this. That's a serious problem. I cannot use this.
In the first one,
What?
the first one, we're doing the second one.
Oh, I'm sorry, I'm looking at this. Are you looking at that? Have you been looking at that the whole time?
No, not from
Oh, okay. Oh boy, we got a problem. Right now I'm looking at this. Okay. So I'm saying, yeah, there is a problem. I cannot go to brackets. Okay. So where should I go? I cannot go here. I should go to T. Now, when is the language called unambiguous? Here's a language. A language is said to be unambiguous if what? There is a what? At least one unambiguous grammar for it. If there is an unambiguous grammar for it, the language is unambiguous. Of course, a language itself will be ambiguous if what? It will be correct to say if there is at least one ambiguous grammar for it? No, because then this guy will be both ambiguous and unambiguous. A language is unambiguous if there is at least one unambiguous grammar for it. And the task will be, can you find it? Because some of the grammars will not be quite good. They will be ambiguous. If a language is unambiguous, you should be able to find at least one grammar which is unambiguous. Then you say, okay, the language is unambiguous, I can parse it. Is every language in the world unambiguous? No, unfortunately not. There are some languages inherently ambiguous. When do you say that the language is ambiguous? Huh? If it what? If it has no ambiguous grammar. What? If you cannot find an unambiguous grammar for it, then it's ambiguous. Right? If all the grammars that can possibly define it are ambiguous, right? There is no such thing. The language is ambiguous, which means there will be at least one phrase in that language that can have double meaning. It might mean this, it might mean this. Right? I can derive derivation trees to get double meaning. Okay? Like a lot of the context-sensitive languages and things like that. Natural languages, you can always find a sentence with double meaning. That's why so far we don't have a compiler for natural language. There's a reason for it. All right. So some languages, unfortunately, are ambiguous, inherently ambiguous. You can do nothing about it. I cannot interact with the computer using it because I could, but sometimes he will give me the wrong results. Right? I'll say one thing, and he will do what I did not mean to do. He has two meanings. Who knows what derivation tree he will produce? So he will not be stable. But maybe that's an AI guy, an AI machine. Humans are not stable. Right? When I give you instructions, you don't always follow them, right? So, and there are misunderstandings and things like that. Okay, that's why natural language is in the realm of AI. Algorithmically, we don't. It's not part of a theory of algorithm scores. Right? We have to go to AI to do that. Okay. Now, there are some languages you told me before that are not context free. They cannot be recognized by PDAs. One step. Well, for example, A and B and C. But you know, like we give the exercise to the freshman, write the program. So if the string is A, B, C's equal number, he will write one here, right? To recognize those things. So this is a computable program. There is a program, there is an algorithm for doing it. So PDAs cannot be it. PDAs cannot be equivalent to algorithms. There are some algorithms that are not PDAs. Okay? So there must be an extension of PDA. PDA is one type of algorithm that solves some problems. Okay? Well, the extension is the Turing machine. Turing machine is equivalent to the concept of algorithm. Okay? Turing machines and algorithms are equivalent. Turing machine is a theoretical construct to describe what an algorithm is. Okay? That's what an algorithm is. And by knowing what the Turing machine is, you know what the computers can do and what they cannot do. This is an interesting question. What problems can we solve with this guy using this machine? And what problems we cannot solve? Can we solve anything? No. I would like to poke him the question, is there a God? Okay, go ahead, can calculate, can answer the numbers, whatever. Can I solve anything I want? That's it. That would be nice. Okay. Well, are there some problems I cannot solve? Why I cannot solve them? Can you prove you cannot solve them? I cannot solve them because I'm not intelligent enough to write the appropriate algorithm. Okay? Or they are not solvable. Can you prove they are not solvable? And yes, there are some problems. How do you address these questions? Are there problems that are solved? Are there problems that are not solved? Well, that theory addresses this question. It will help you to investigate these type of questions. So anything that we do must be a Turing machine. If you cannot build a Turing machine, you cannot do it. You cannot program it. You don't have an algorithm. All right, let's see what is a Turing machine. Turing machine is an extension of the PDA, right? But here are the differences. Again, you have the tape. The input you are going to process to find a solution or whatever, to give me an output, is on the tape. You have an alphabet, sigma. Solutions to a problem, as we said before, are patterns, strings. Everything reduces down to a string, down to a sequence of symbols. That's the only things I can process. Okay. So the input is going here. Let's say you said A, N, B, and C, N, so I'll start. Now, I will put on the tape a special symbol to indicate the start of the tape. And you will see why. In the PDAs, I did not need the symbol because on the tape you can only go forward. You have to read and process, or ignore and process, stay there and process. You can only go forward on the tape. Here is the first difference in the Turing machines. You cannot, from the current position, you can go forward on the tape, read the next symbol, or you can stay in the current position. You can read the symbol, use it, and stay. Not ignore it and stay like the PDAs, read it and stay. Or you can go backwards, rewind the tape. Rewinding is allowed. That makes huge difference. So if you allow rewinding, how would you know you're at the end of the tape on that side? You need a special symbol. So let's say $sign is not in the alphabet. Okay. will use it to tell you the end of tape, the start of tape. Okay. So then I have something like AA, BB, CC. We don't want to worry about how much memory you got and stuff like that, so we'll assume you have as much as you need. So we say the tape is semi-infinite. Don't worry about running out. So after there is another marker, let's say blank is not part of sigma. We'll use this marker to indicate a blank. So after your input, you have all blanks. The tape is pre-initialized with blanks. You don't need to write the tape. Okay, then what do you have? Like you had in the PDS, you have a set of states. You have the clock. One of the states is the starting state. Okay. One of the states is designated as the halting state. That corresponds to the exit statement in your program. The program halts, the algorithm stops. And the algorithm is actually the transition function. This is the algorithm. Right? It tells you how to process the input. What is the transition function like? If you give me the current state I'm in, which cannot be the halting state, so you are in stage minus h. If you give me a non-halt, the current state, because if you're in the halting state, you don't apply the transition, you're done. Okay, you're in the current state, I'm here. And if you give me the current symbol on the tape, what are you looking at the tape, the current position? So you give me the element of sigma, this is the current symbol. The algorithm, the transition function, will dictate to you what to do next. So she will tell you what is the new state. Oh, go to Q1. If you see an A here and you're in Q0, okay, go to Q1. So that's the new state. And it will give you the other ability you have, besides moving back and forth on the tape, is to write on the tape, which you cannot do before. You cannot write on the tape. You have, if you wanted, you could push on the stack, but okay. So you have to tell me, based on the current state, the symbol you're looking at, what is the next state? That's the next state. And you have to give me what symbol to write here in this position before I move. So that's the symbol to write, the new symbol. If you do not want to change the symbol, write itself back there. So if you're in Q1, in Q0, and you see a B, write a B. Okay, I will change it. Or write an A, I can change it. Write a blank, I erased it. And then tell me, after you wrote the symbol here, if you should go left, right, or stay on the tape. That's your three options. You can tell me how to move. Left, right, or stay. L is left. Okay. Left, right, or stay. That's the transition function. Okay. Now, you can give the Turing machine, right, doing a matrix, the transition matrix, or you can use the diagram with the states, the nodes, and the arcs. Let's use the diagram. Let's say I give you this. Here is the starting state. I start. Well, when you start, you see the dollar sign. That's where you're at, the starting symbol. Okay. If I see an A on the tape, what do I have to tell you? If I'm in this state, I have to tell you, based on what the current symbol is, what the next state is, and what do I do on the tape, and how do I move on the tape. So the notation is, if I'm in this state, if I see an A on the tape, actually, let me tell you if I see a dollar sign first. If I see a dollar sign on the tape, I just gave you a Turing machine, right? What, can you see it from there? What will it, my question is, what will it do? What will this program do to the tape? Clear all the symbols. And when he halts, where is the reading pointer? The start symbol. So he will take whatever you gave it in the tape, assuming the alphabet is A's and B's. Right? He will clear them, he will replace them, go right, no matter what A and B is, what symbol you see. When he hit the blank, he will start going left, L, with the blank, until he sees the dollar sign. Okay? Then she will go back after she deleted them, the dollar sign, she will stay and halt. So what this machine will do, it will take this input, whatever the input is, and when she will start here, and when she's done, you will have this on the tape. She will still be here, but she will have erased everything up to the first blank. Right? That's part of the tape. Turing machines are algorithms. You just wrote a program so that if you feed it this as input, it will give you that as output, blank. If you feed it a string here as input, that's not a program. So this program is not very useful. He gives you the empty string out. You just wrote a program that no matter what the input is, A, B, 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 A, empty string, B, 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 A, 1 million symbols, empty string. Right? And you wrote it by processing the input as an array. You know, if you want to simulate it, to write a program exactly to do this Turing machine, of course it would be an array of move I++, okay, and so forth. Right. Now it turns out, of course, there is a very simple program to do the same function, right? Print empty string, print nothing. That's the program. This is the constant function print nothing, no matter what the input is. If you want, you can read the input. C in input, right? C out nothing. That's what you just did. Right? Well, there might be two programs that solve the same problem. And one is similar than the other, but they both are equivalent. You know that. That's why your programs in the program assignments are supposed to look different. And if they look exactly the same, then we start thinking, hey, what's going on here? Like, there are an infinite ways to write a program. Yeah, I mean, infinite, but they're finite because the symbols are finite. But maybe they're infinite. I can take any program and start sticking irrelevant statements in it. Okay? So this is, but in a Turing machine, that's the function C out the empty string. It's complex. Okay? I'll call it Fortran. Okay? I want to define, how do I design it? I want to build a grammar to syntactically define a sentence. Okay? Well, what kind of statements do I need to have in my language? An assignment statement? Yeah, sure, because I can do memorize things. An input and output? Okay, yeah, sure. But what else? In most languages, they have control structures, like if, nested if, whatever, conditionals. Okay, most languages have, what else? Loops. Okay, while loops. Okay, I mean, why? What's so special about ifs and while loops, right? Okay, Because if an algorithm is a Turing machine, to be able to implement the algorithm, what do I need? This is a while loop right here. As long as you see an A, to replace the blank, move right, A. You see a blank, that's the exit statement of a while. That's a while loop right here. If Turing machines is what they are, well, what do they have in them? While loops and ifs. You should be able to check if you have an A or a B, that's an if statement. Where's the current inputs? So the arcs are ifs, if you see an A, you know, yeah. That's what you need, ifs and while loops. Once you have if and while loops, you can do anything because you can do any Turing machine. So those are the necessary structures. Because you might wonder, oh, I built my language, man, I only have if and while loops. Maybe there are some problems I cannot solve, you know. Are those enough? I'm missing something, you know, right? I don't know if my language is powerful enough.
And last time you understand the definition?
No. How do you connect these two languages? Finite state atoms are Boolean functions, right? PDAs, Boolean. You terminate in the final state, you read the whole string and the stack is empty, then the output is yes, it is accepted. Now, Turing machines are not necessarily Boolean because they rewrite the tape. The input is on the tape, the output is also on the tape. How do you relate Turing machines to languages? Well, you got to make a definition. You say a language is recognized by a Turing machine if, okay, a language recognizer is Boolean. You will either say yes, it's a legal, syntactically correct string, or no, it's not. So how would you do that? Well, Turing machines could be Boolean functions. So you will say a language is decided by a Turing machine. The language is recognizable. If what? Here's a possible way to do it. If you can build a Turing machine that works as follows. When you start the tape with a string contained in the language, the Turing machine will process it. And when she's done, she will replace the whole string by yes, or let's say the symbol y, or 1 for true. Okay? But if the string is not in the language, when she's done, she will replace the whole string by no. Let's say n. Okay? So that's the definition we'll take. So language is Turing decidable. If you can build a Turing machine. In our notation, $sign is the start of the tape. So, so a language is Turing decidable if you can build a Turing machine. So when you start the tape here, when the Turing machine is done, she will replace this by black, this by black, this by yes. Replaces the whole string by yes. And she halts at the $symbol. If the string is not in there, no halts at the $symbol. Okay? Now, we have the ability to recognize other languages that are not codex-free this way. So you can build Turing machines for them. Okay. So some languages will be Turing recognizable. Okay, we'll do it in the future. If you take this one. Okay, is this language codex-free? No, why not? How do you know?
So he's telling me he cannot build a PDA for it with this type. Yeah, because I can prove it using a public.
It turns out this is Turing recognizable. You can build a Turing machine to recognize this.
Now somebody might wonder, maybe every language is Turing recognizable, right? You guess that the answer is no. There are some languages that are not, and that's correct. And we'll see some more examples in the future.
All right, let's do an example. In the notes you will find this one.
The language, a number of ones, a string of ones, but odd number of ones. Take the language of odd number of ones. Is this Turing recognizable? If you say yes, the way to prove it will be to build a Turing machine. If you say no, that's a more difficult proposition. We don't know how to prove it yet. How do you show there is no algorithm, right? That's difficult. Okay, but this will be Turing recognizable, odd number of ones. Before even building the Turing machine, I can say, yeah, that would be Turing recognizable. How do I know that? Let me ask you this. Is this context free? Actually, let me ask you this. You said yes. Is this regular? You also said yes. Okay, show to me this language is regular. How do you show it? Build an FSA. Or build a what? A regular expression. Or build a right linear grammar. Okay, you want FSA?